Welcome to week 6 of Honors Physics e-learning. This week will involve our chapter with work and energy. All right, so this week you'll be learning how to calculate various forms of energy and also determining the percent efficiency in any energy transfer. All right, this week you will be going through these learning targets and success checklists within these notes. um, you'll also be completing your week 6 practice Google form as usual. By doing those two things, you should be able to calculate GPE, KE, and SPE given a whole host of variable inputs, including mass, height, velocity, spring constant, and or stretched or compressed distance. You'll also be able to equate work done by a force to an object's change in energy, and we will specifically focus on GPE, KE, and SPE. Lastly, you should be able to find the percent energy transfer or efficiency while using one of three simple machines: a pulley, a ramp, and a lever. Right. Lastly, you will be beginning a project that will span weeks 6 through 9. You will have a choice on whether you want to create a Rube Goldberg device or a pinball machine. Please look at your document in Google Classroom for more details. Now, the three forms of energy that we're looking at here, and all energies in metric units are measured in joules. 4,184 of these is equivalent to what you know as a food calorie, right? So if you look at the back of a food label and something is 100 calories, the number of joules in that would be 100 times 4,184. Okay. Now, kinetic energy is energy of motion. All right. So an object must be moving. So notice it depends upon velocity. So in this table, we kind of have some color coded things to help it make it clear to you, right? M is mass in kilograms, V is velocity in meters per second. Click this interactive practice here in order to remind yourself how to go through and calculate KE. Gravitational potential energy is energy stored due to a fact that an object is high in the Earth's gravitational field. So notice it depends upon height. And this height is measured above some reference level. Usually we use the ground. So you also need to know the acceleration due to gravity, right? So in essence, this is the weight of the object multiplied by its height. This also leads to units of joules. Click this interactive to refamiliarize yourself with GPE. Lastly, SPE, spring potential energy, is the energy stored in a spring, whether it is stretched or compressed. The X in the formula here represents that distance measured in meters. The K is your spring constant measured in newtons per meter. Remember that a high K value means you have a tight spring. A small K value means you have a loose spring, right? You can click this interactive down here. It's an energy conversion lab where stored energy in a spring is transferred into kinetic energy of an object launched forward. That will kind of review both these forms of energy with you. Now, whenever forces are applied to objects, they do work, okay? And work is the product of force and displacement. Force and displacement are vectors. Notice they are bold-faced here, all right? We're not going to go too deep into the math here, but this multiplication is what's called a dot product. So when you multiply two vectors, all right, the kind of the bottom line is if these two vectors are in exactly the same direction, when you multiply them, you will get a positive work done. However, if these two vectors were in completely opposite directions, that means the force is doing negative work. So you'd still multiply the two numbers, yet the result would be negative. Lastly, if these two vectors were perfectly perpendicular to each other, if they formed a 90-degree angle, then no work is done by the force. There's no need for you to do any math. The result would be zero. Okay? Now, whenever you have an unbalanced net force, then that net force will cause the object's kinetic energy to either increase or decrease, right? If the net force was in the same direction as the object's motion, it would increase it. If it was against its motion, it would slow the object down. Okay. This is a very nice interactive practice where you are equating the work done by a net force to the object's change in velocity. Okay. Gravitational potential energy, whenever our forces are upward, causing a height change and steadily moving an object upward, that upward force is essentially the weight of the object. And you can see that these kind of give you the same thing, because your upward force is equal to the weight of the object, and the distance it moves is just the height that it gains. All right. So you can see the equation here is just matching those two together. Lastly, spring potential energy is a little bit more complicated, and that's because when you are applying a force to a spring, as we've gone over before with Hooke's law, the force needs to get stronger the further the spring stretches, right? So your force is not constant. So the work done by this force, you'd have to use the average force. All right. So when you go to pull a spring, it would vary from 0 up to some maximum value. If you have a linear spring, then the average force would just be the middle value between 0 and the max. All right. So that work done by that average force will cause the energy stored in the spring equation 1/2 kx squared. Whenever we have a transfer of energy between two different types, that transfer may not always be 100% efficient. Okay. A lot of times, some wasted energy in the form of heat is released. So you can kind of view it with this little diagram. To calculate that percent energy transfer in general, you can just take the energy that you get out of the transfer and divide that by the energy into the transfer, times it by 100 to make it a percentage. As an example, if we had an object at a high height, all right, it's storing GPE, and then it moves down a hill, it will be changing its energy into GP, or from GPE to KE. In that process, the object is probably encountering some friction down the hill, and some of that energy transfer will involve energy released in the form of heat. All right. So if we do the math, this object, 40 kilograms, 5 meters high, if we're assuming acceleration due to gravity of 10, we get a GPE of 2,000 joules. However, at the bottom of the hill, the object's moving at 8 meters per second. That allows us to calculate KE. Here we only get 1,280 joules. Notice that that is not a 100% transfer. If we take the ratio of those energies, we get 0.64, which is equivalent to 64%. Now, simple machines, all right, we're going to focus on first-class levers, ramps, or inclined planes, as well as pulleys. Their purpose is to allow you to lift an object at a lower force than what you would need without the simple machine. However, it does not allow you to do less work. In many cases, you do more, right? However, if you have what's called an ideal machine is one where there is no energy loss due to heat or friction, right? So if we kind of look at this little flow here, if we have energy in, all right, that's going to be turned into the energy we get out. But for an ideal simple machine, the energy loss would be 0 joules. Each of these pictures is interactive. If you click on them, okay, they take you to a website where you can run through a lab with each of these 3 simple machines. Okay. However, in many cases, simple machines are not ideal. There will be an efficiency less than 100%. There will be some energy loss. Okay. In order to calculate the energy that gets put into a system, that's the work done by the force, right? So for in and out, it's the same exact equation. We just need to use the appropriate quantity. Okay. Um, this is where we also talk about the advantage of a simple machine. The ideal advantage is the ratio of your input distance to output, while your actual advantage is the ratio of the forces, right? Because that is the purpose of using the machine, is to have your force multiplied. All right, so one example to see this run through. All right, object is lifted with a combination of pulleys. The object weighs 450 newtons, but the person is able to lift it with only 75 newtons of force. The trade off is that he needs to reel in a whole lot of rope, 16 meters, to only have the weight move 2 meters upward. Right. So if we want to run through this, the ratio of the distances is 8. That would be the ideal advantage we get if we had a 100% efficient machine. However, not all of the energy was used. There was some loss, right? And we can see that because the actual advantage is not 8, right? The ratio of the force out to the force in is only 6. If we run through and calculate the energy put into the system, right, we have the input force and the input distance multiplied. We put in 1200 joules of work. However, the energy out of the pulley system is only 900 joules. So notice there is a loss of 300 joules of energy, so that when you take the ratio of the energy out versus the energy in, notice we get 0.75 or 75%, which is also the ratio of the AMA to the IMA. Okay. Um, this applies across all different types of simple machines. You can apply this also to an inclined ramp as well as a lever. Okay. Good luck starting your project and see you next week.